Okay, can you hear me? It's okay. All right. Have you recovered from this morning's lecture? Uh, it's hard to sit still for the whole morning. So today I will also give you some exercise, not as fun as yesterday, unfortunately. Uh, Yesterday was actually the exercise. You actually derive a very important result, and I hope you appreciate that in the end, such an important result, which supposedly explain all the structure that we see today, is a very simple calculation. Um, so what I want to do today is I started with a summary of yesterday. This is really the only thing that you need to remember from yesterday. It's all here. Uh, and it's about a massless scalar. I call it a spectator, meaning it doesn't really participate in gravitating, changing the metric. It just basically live passively in this expanding background. And it turns out such a scalar degree of freedom, even if we were in the vacuum state, so the ground state, there would be inevitable quantum fluctuations. And basically this calculation tells you what is that fluctuation. And in fact, let me just add one thing uh, that you should always kind of think of this heuristically in the following sense. This power spectrum is defined from basically taking 2 powers of phi, yeah, in momentum space. And this power spectrum has dimensions because it's really k cubed p of k that is dimensionless. And so the dimensionless, if you want, what is the dimensionless? Actually, let me not call it dimensionless, but you should always think of it this way. So you should multiply your power spectrum by k cubed and take the square root. What is that? That is basically if somebody asks you, well, what is your RMS fluctuations in this universe where you are in the lowest ground state possible? How big is your fluctuation? This is how you should answer that question. You should say, take the power spectrum, multiply by k cubed. This k cubed basically comes from the measure, the 3k. You take the square root, and if you do that, this is basically roughly h at late times, yeah? Sending eta to 0. And so this really is the upshot that if you have some light degree of freedom that has mass dimension 1, such as this scalar, somebody asks you, well, what is the root mean square fluctuation? How big is that amplitude? It's just h. It's just given by Hubble. That's it. That's the only thing you actually really should remember. Okay? And this is from yesterday. Very good. So what I want to do today is now we transition to talking about the metric perturbations. No? So this is all nice, but this is just some scalar living in that background. At the end of the day, we want to account for the fact that whatever live is driving inflation, it also causes metric perturbations. So let me tell you just very briefly about the kind of picture we have in mind. So what is the, let's just write down the Lagrange, the action. No? What is the action we are talking about? Well, we have in mind something like this. Uh, first of all, there's always gravity, and so I'm going to have the Einstein-Hilbert action right there. R is the Ricci in 4 dimensions. And I'm going to imagine that in this universe, there is one field that dominates the energy density of the universe, and it's called the inverton. And you can write down actually many possible um, terms for it, but we'll do the simplest one, which is the following. In case you wonder about my sign, although very often I'm not very careful, I'm using minus plus 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 here. That's why there's a minus here. Okay, and V is the potential for this phi. So now I want to emphasize phi is not a spectator. in fact, is the inverton, okay? Perhaps I should give it a different name, but I'm just going to use phi. Okay, it's the inverton. And when I say it's not a spectator, what do I mean? So let me draw the potential. So this is the potential for phi as a function of phi. Usually what people have in mind is something like this, that this potential has a large, associated with there's a large cosmological constant, and there is a part that is very flat, and during inflation, your scalar field probably lives somewhere here in the flat part of the potential. The potential have a very small slope, so the scalar field is slowly rolling down this potential. But it's so slowly rolling that the energy density, if you ask what is the energy density associated with the scalar field, ignoring spatial gradients, you would just say this, no? Yeah, so ignore spatial gradients for now. Suppose you are just looking at the homogeneous part of the scalar field. The energy density is this. If this is very slowly rolling, and if this is very flat, this is really like a cosmological constant. And when people talk about inflation, they have in mind that this cosmological constant, basically this value, is very big, dominates over this kinetic term, because the scalar field is so slowly rolling. And then it drives inflation. So this is what drives, this drives inflation. Drives inflation. And in the limit, this is exactly a constant, and this is completely negligible. Then you can show A proportional e to the ht, like what we talked about, or like what we said yesterday, in conformal time, it will be 1 over h eta. Okay? That's what we have in mind. This, and I call this not a spectator because it is really the energy associated with this field that is actually determining the metric. So it's not a spectator anymore. It actually has a role to play in determining both the background metric and, as we will see, the metric perturbations. Any questions? Basically, this is the setup. Yeah? And here's what we are going to do. We are going to say, well, this scalar, let me use proper time. So I'm going to use t here. I hope you still remember the difference between proper time and conformal time. I'm going to talk about this. In general, in your universe, your scalar field, including the inverton, should not be completely homogeneous. There will be fluctuations, just like the kind of fluctuations we talked about there. Even though you are in the ground state, you cannot help but have quantum fluctuations. So in general, this is a function of time and space. We are going to say that for the most part, if you average over space, you can define a homogeneous component, which I'm going to call phi bar. And then there will be fluctuations. And we are going to assume the fluctuations are small. These are small fluctuations. This is the homogeneous background, only depending on time, which basically tells you this over time, this scalar field is rolling down the hill. But these are the fluctuations that we'll be interested in, right? So the first thing we are going to do is to say, remember, because we are talking about gravity, in gravity, it's a gauge theory, which means we have freedom in gauge, meaning the choice of coordinates. So we have freedom in choice of space-time coordinates. These 4 coordinates. So you have actually 4 gauge freedom in your choice. So we are going to now make our first choice. We are going to choose a time coordinate, and this is what we are going to do. It's often called unitary gauge. Unitary gauge. we are going to choose something like this. So let me actually plot it. So I'm going to draw a space-time diagram. So this is time, this is space. This is your equal time surface. It will be something like this. On this equal time surface, phi looks like this. That not only does it have this pure function of time part, which is the dominant background, it has this fluctuation which depends on location. So it kind of look like this maybe. If you plot it, phi might be higher here, and phi might be lower here, and so on. Yeah? So you can kind of imagine that in your head. So unitary gauge is something very simple, is to say, I'm going to change my time coordinate to completely zero out this fluctuation. You understand what I'm saying? So I'm going to choose some other time coordinate, for example, something like that just track the fluctuation so that on this surface, in this weird time coordinates, now my phi is in fact a pure function of time. You understand what I'm saying? So I basically choose t such that delta phi is actually equal to 0. So choose that surface. Now this sounds abstract, but concretely what do you do is very simple actually. So you say the following. So you say, instead of this, I'm going to consider phi at t plus delta t, where this is the change in your time definition that you are going to do. And if you expand this out, this is equal to t plus phi dot delta t plus high order things. If you think about it. So I'm suppressing the spatial dependence. There's spatial dependence here. But the thing that I want to emphasize is if you take a field, you redefine your time. Suppose you call this your new time. This is your new time coordinate. This field configuration is related to the old one in this particular way, as you see, just by a Taylor expansion. And so all you need to do, therefore, choose to cancel. Basically, you make this choice. Now, if you assume delta t is a small time diffeomorphism, a small change, then you can actually say, well, actually, you can just put this on the background. This is the background phi bar. Time derivative times delta t. I choose this to basically zero out whatever delta phi exists. And that choice would accomplish, this would imply delta phi in the new t plus delta t coordinates vanishes. Is it clear what I'm saying? This is what you can do. Okay? Yeah, yeah. Yeah, we are assuming anything associated with this and its derivative is small compared to the background. Yes. Yes. Excellent question. Excellent question. I think we will actually see this actually more explicitly how that works. In a sense, what I'm saying is the following. I'm just basically comparing amplitude. So you should think of this as a small quantity, and you should think of this as a small quantity. And so basically, what I'm saying is, suppose you want to include that part, which is what you are actually asking about. This one, if you don't put the bar on top, there's actually this. Yeah. So you are worried about the fact that, well, this might be actually varying rapidly with time, right? Yes, that is true, but then you just ask yourself, well, how big is this amplitude? So you always consider a regime where this amplitude is sufficiently small, multiplied by another very small thing, so that this is really second order. And what you are comparing at the end is not so much comparing this against that, you are comparing this against that. That's what you're comparing. Okay? So as long as the amplitude of delta phi and the amplitude of delta t are both sufficiently small, so this is second order, then that would be small compared to this. But yes, you're right, I have to keep in mind this is actually not delta phi, but delta phi dot. But you can basically go to that regime where the amplitude is sufficiently small, then you ignore this, compare against that. Does that make sense? Other questions? Other questions? So pictorially, this is what I meant. Just mess around with your equal time surface. Instead of this flat original equal time surface, make it curve around. And you curve around in just such a way to make this part actually go to zero. So on that surface, now, there's no spatial fluctuations for phi. Okay, so unitary gauge, in unitary gauge, this now becomes true, at least to first order. We are going to do perturbation theory in small fluctuations. Any questions? Okay, so that fixes this degree of freedom, the time degree of freedom. How about the spatial degree of freedom? The spatial degree of freedom requires a little bit more work, and I'll just claim the result is the following. Let's look at the metric. So the metric is, of course, a 4x4 matrix, but I'm going to focus on the spatial part, the Gij. So for me, I and J are the spatial components. And this is equal to what? Well, there is always a background, which is a squared. If there were no fluctuations, we would just say your Gij is a squared times delta ij, right? That would be the background. A, remember, this is the scale factor. But we will now want to consider the fact that there could be fluctuations. So what would the fluctuations look like? For example, I could multiply this delta ij by 1 plus something small. That something small is usually called zeta. And by convention, there's a factor of 2 there. So this is small, okay? So this is one possible fluctuations in the spatial component. So this is the fluctuation in the trace of the spatial component, right? So this is a 3x3 matrix. This is just purely along the diagonal. And certainly the metric can fluctuate that way. It's purely in the trace, okay? But if you think about it, as a 3x3 matrix, there are probably other ways to fluctuate, no? There are many ways to fluctuate. How about the off-diagonal components? If you are talking about scalar perturbations, for example, there could be components that looks like this. Let me try to write this way. Let me for now put a gamma ij here, and I will talk about what this gamma ij represents. So this gamma ij, for it to be describing some metric fluctuation that is separate from the trace, so you probably want this to be the trace-free part. So this is the trace-free part. Gamma kk equals 0. In this part of the lecture, I'm going to be a little bit sloppy in my indices, but let me tell you exactly what I mean. When I write these ij indices, and I say gamma kk, I actually mean sum over k and k, and I don't bother raising and lowering indices. When I talk about these ij indices, they are raised and lower with just delta ij. Okay, so I don't bother even writing down up and down. So take the trace. So if you want to be more precise, this is what I mean. You sum over k, that is equal to 0. So this part of the metric clearly is completely independent of this part. This part is the trace. This you can write down in general. Yeah. Now, given this gamma ij, you can further decompose it. And I want to at least remind you how to do that in simple cases. If I give you a three-dimensional vector field, so let me do an example. If I give you a three-dimensional vector field with indices labeled by I is 1, 2, and 3, a vector field in three-dimensional space, you know you can always decompose it into a gradient and a curl. Remember that? Yes? That can always be done. So you can say this can be written as the gradient of something. Doesn't matter, you call it, let me call it chi, plus an additional part, which is actually a curl part. So I'm going to call it Vi transverse. Transverse in the sense that this is curl. That means its divergence is 0. Yeah, given a vector field in three-dimensional space, you know you can always make this decomposition. Yeah, and so what you want to do here is to do something similar for this metric. This traceless metric, 3 by 3, let's do a similar decomposition. But now it has two indices instead of one. So this is what you do. So you say your gamma ij. What is the analog of this gradient part? Well, you can probably write this way: di cj plus dj ci, just to make it symmetric. So think of this part as the analog of the gradient part. The reason why it's no longer a scalar is because you have two indices here. So the analog of this gradient has to look like that. So gamma ij can be broken up into the gradient of a vector plus something that is transverse, just like here. And the transverse condition would be to say the following. You say di gamma transverse ij equals 0. That would be the transverse condition. Does that make sense? And you recognize what this is. This is something that has 0 trace and is transverse. This is the gravitational waves. This is what we call the tensor mode. Yeah? Yes? And so in general, your metric degree of freedom, again, has the trace-free part. The trace-free part contains a transverse part. This is the gravitational waves. This is the tensor mode, gravitational wave or a tensor mode. This is the scalar mode. And now let's just talk briefly about this part. Well, this part, what do we do with it? Well, this part, fortunately, we have gauge freedom. So we have used up the time degree of freedom to define unitary gauge, but we have complete freedom in choosing our spatial coordinates. And we choose our spatial coordinates to zero this out. Why can you zero this out? And this I appeal to what you might have learned in GR. I hope you remember. If you do a gauge transformation, x mu going to x mu plus z mu. Let me just do I. Let's focus on the spatial component. I'm going to do a space diff. You know the change in Gij is this kind of combination, no? I hope you recognize that, yeah? Remember what you have learned in GR. The gauge transformation associated with the space diff would generate this change in Gij. And look, this actually have the same form as this. The only thing you have to be careful about is these covariant derivatives. But you can be careful and convince yourself this indeed you can zero out. Okay, I'm not going to do that for you. You can do that, but again, keep in mind to be careful doing that. You are always doing perturbation theory. You are saying, Well, this is small. When I do this covariant derivative, I can just do this on the zero order background and not have the fluctuations, because including the fluctuation will give me second order things. So provided you have keep that in mind, you can convince yourself this works, and so you can zero this out. So this is zero out by choice of your spatial coordinate, basically. Does that make sense? And so at the end of the day now, you have used up all your gauge freedom, time and space, and your metric now is really just this one that I'm writing down for you, at least for the spatial part. So far only for the spatial part. There is a scalar that lives in the trace, and then there is this part. Now, strictly speaking, I should just put a t, but from now on, I'll just even forget about the t. Whenever I write gamma ij from now on, I mean the following. I mean a gamma ij that's traceless and transverse. So it is the gravitational waves, it's the tensor mode. So the spatial part of the metric now have one scalar and one tensor mode, yeah. Yeah, you should be more careful. So I'm not being super careful about basically this derivative, but you can. On a curved background, in general, you do this decomposition using covariant derivatives, exactly as you said, yeah. Okay, any questions? So that is the setup now. So let me just say this again. This is what you start from. It's supposed to describe the theory of a universe that actually gravitates, where the gravitational field is determined by the energy associated with this scalar field. We assume this scalar field is mostly homogeneous, slowly rolling down off the hill with small perturbations. We choose a time coordinate to zero this out. So we have zeroed this out. And furthermore, we choose spatial coordinates so that the spatial part of the metric look relatively simple. It has a scalar degree of freedom, which is sourced by the inflaton, and gravitational waves that just live in this inflating background. Yeah. They are going to be vector components. They don't, by my gauge choice here, they don't live here. They live in the other component of G mu nu. But it turns out, because we are considering this simple theory where gravity is really just sourced by this scalar degree of freedom, it turns out we won't have actually the vector modes. But in general, they are there. Yeah, they would live in the G0I components in general. Questions? Well, the fluctuation in the scalar field has been gauged away in the inflaton. The fluctuation in the metric survives. They are here. Does that make sense? Yeah. And that's important because you cannot gauge everything away. The fluctuation, because you have chosen a unitary gauge, the only fluctuations now that you have in those coordinates are the metric fluctuations. And that's what we are going to focus on now. It's basically these, the scalar mode and the tensor mode. Okay. Let me talk a little bit about the other components. No? There's G00 and G0I, so you might wonder, well, what about them? I won't say too much about them, actually. I will just say the following. This is what I'm going to say. So how about G00 and G0I? In particular for us, actually, what is going to be important is that if I write down my metric, so actually let me write down my metric. My metric looks like this, right? This, I have basically minus 1 minus delta G00 dt squared plus g0I dt dxi, and usually there's a factor of 2, and then I have basically that plus a squared delta ij. Where this is transverse traceless, okay, TT. This is the full metric. So let me say a little bit about these. As you can see, the background is just this 1 minus 1 dt squared plus a squared delta ij. Of course, you have to contract with the xi dxj. That's the background. Anything else is fluctuations. For that reason, it's helpful to just think of this G0I as a fluctuation, because to zero order, there's actually nothing in G0I. So I'm going to go with delta G0I. So this is all small, 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 and small. These are the small things, yeah. Okay, and now if you take Einstein equation, you can write down basically the 0, equation, the equation of motion by varying delta G00. You can also write down the equation of motion by varying delta G0I. And so it turns out, and this I will just claim it. It turns out you can solve the delta G00 and delta G0I equation of motion to express both in terms of zeta. Okay, I'll just claim it without actually showing it. Yes? But I hope this is semi-intuitive, because you have seen something like this in Maxwell. Let me remind you how it works in Maxwell now. In Maxwell, let me ask you, what is the A? So you have A mu, A0, and AI. What is the A0 equation of motion in Maxwell? What is it? The A0 equation of motion. That would be the analog of the delta G00 equation of motion. So example, analogy, huh? I'll just do an analogy. In E&M, the A0 equation of motion is Gauss' law. Yeah? It's basically this, no? It's di fi0 equals, I can never remember my sign, so I'll just do proportional. It's proportional to the charge density, no? Yes? You agree? That's just Gauss' law. This is the electric field. Divergence of the electric field is the charge density, okay? And of course, this is, what is this? This is di A0 minus d0 AI. You agree? Yes? And look, if I tell you what AI is, including its time and spatial dependence, you can take derivative, plug into, basically plug into this equation and solve for A0 in terms of AI. In fact, if you look at this, what you have is a Laplacian A0 sourced by basically this, no? The 0 divergence of A, and then plus rho. Yeah? So you can invert the Laplacian in principle, solve for A0 in terms of that. That's all I'm doing. But at the level of gravity, the equation is just more complicated, but the same idea. You can go ahead and do that. Once you do that, you go back to this action and you plug in your expression for delta G00 and delta G0I, and so you have basically eliminated them. And so you should be able to write this action now in terms of just, once you do this, then now the action can be written in terms of purely zeta here, gamma ij, which now is for me is transverse traceless, is the tensor mode. And that's it. In terms of fluctuation, there's not, in principle, there's delta phi, but because I've chosen unitary gauge, there's no delta phi to talk about. And so you are going to end up with an action that's relatively simple in terms of only zeta and gamma ij. Now, doing that is actually a lot of work, so we are not going to do it. If you want to see this done very explicitly, look for this paper by Madasena in 2000, I think. You can find it's about primordial non-Gaussianity. So he discussed that. You do many integration by part and so on. You get it, okay? And I'll just tell you the answer. But I hope conceptually you can see how you might do it yourself. And for the good of your soul, you should try it once. Do it for yourself, okay? Any questions? That's the idea. So now I'm just going to write down, I'm just going to write down that action, which is now purely in terms of these 2 degrees of freedom. These are the only 2 things, once again, that can depend on space. There's no delta phi in this gauge, okay? But before I actually go on, let me just mention there's one equation. So in this procedure, it turns out there's one thing that is important. And because I want to keep it around, I'm going to write here. From the delta G00 and delta G0I equation of motion, there is one thing that's important. It turns out the following is true. If you take Laplacian, again for me, this is just a flat space Laplacian. This a half H delta G00 plus zeta dot turns out to be 0. If you look at the equation of motion, you can show this is true. And this actually is something we are going to use at some point, okay? So I'm going to keep this here. So this step is a bit cumbersome, but along the way, you will find that this equation, basically. And that is going to be important for what we want to talk about when we talk about symmetries. Okay? Any questions? So now we are going to write down this action. No? Once we write down the action, then I'll give you an exercise. Okay, we do an exercise. Okay, so I'll tell you the action. So the action, we are going to just completely eliminate the 0 order thing. We are going to focus entirely on the fluctuations. So the action for the fluctuations is the following. And I want to give you exactly all the correct coefficients. So let me see. Okay, it's right here. So sorry for going back and forth between conformal time and proper time. This is conformal time eta. Remember, when I do prime, I mean conformal time derivative. This is zeta minus di zeta. So let me just do it. Let me just do it this way, square. Okay? And I hope you appreciate this. This looks rather like that, up to some factor. Okay? Yes? So that's for zeta. Let me call this the zeta action. There is the part of the action that has to do with the tensor waves, the gravitational waves, and they look actually very similar. It's actually the same. structure, and is 1/8 m Planck square a square. And in here, the structure is the following, I, J. When I have repeated indices, even though I don't raise and lower them, you should understand them to be sum over, okay? This is sum over. And then you have basically this one. Okay? And I hope you also appreciate this also look rather like that, except for the indices. Look rather like this spectator scalar. You understand? So this is the claim. This is quite a bit of work to get here, but I've sketched out the steps for you. I hope at least you find it, you can imagine doing it yourself. Okay, any questions? Okay, sorry. I should have defined that. That's called the slow roll parameter. Thank you for asking. What is that? That's the question. Epsilon is defined to be the following. It's defined to be minus h dot over h squared. The dot is proper time derivatives. What is that about? What is this epsilon? Let's think about that picture that I drew. I have in mind a scalar field that is slowly rolling. As it slowly rolls off the hill, the potential actually drops, which means the Hubble is not a constant. Hubble is going to become smaller. And because it becomes smaller, h dot is non-zero, in fact it's negative, but it's changing very slowly because this inflaton is moving down the hill rather slowly because this is a very flat part of the potential. And so we have in mind, this is called the first slow roll parameter. And it's very, you can think of this as a more small quantity, much less than 1 for inflation. Okay? To give you, if you use Hubble, if you use the Friedmann equation, you can actually show that this is true. In fact, I could have given you as another exercise to show that this is equal to that. You can derive from Friedmann equation. Yes, Friedmann equation is, I guess this is m Planck square over 3, I guess. Okay? You can derive it. I'll just leave that for you to check. Meaning the fact that h dot is non-zero is actually tied to the fact that your scalar field is actually rolling off the hill. So it's not surprising. This somehow cares about phi dot. Okay? Thanks for asking. So that's what this slow roll parameter is. And actually, I think that's worth commenting on. You know, you might wonder, why does the scalar part of the matrix zeta in the action, why does it care about epsilon? What's the deal there? It cares about epsilon because of this, because of what I said earlier about choosing unitary gauge. When I choose my time coordinate to zero out the fluctuation, essentially, what I'm saying is I'm going to use the trajectory of the inflaton as a clock. That defines your clock, yeah? However, if your inflaton is moving extremely slowly, let's take the limit that phi dot somehow is very, very small, which is basically what we have in mind here. Somehow that would affect the way you choose unitary gauge because and in fact, in the limit phi dot actually go to 0, which means your phi is not even rolling, then phi cannot even be used as a clock. And then this whole procedure would not make sense, which is why you find this weird phenomenon that the zeta action would actually go to 0 when epsilon actually go to 0, meaning zeta as a variable, this whole choice of unitary gauge really breaks down if your inflaton is not even rolling, because this whole choice of time using unitary gauge is predicated upon using the inflaton itself as a clock. The feather is actually moving along, even though it's slowly. It's a kind of a slow clock, but you are using it as your clock. Okay, and so the appearance of epsilon here is not an accident. In fact, it's a feature of the way you're doing things. It's good that you asked that question. Any questions? Yeah. Yeah. In my gauge, T is not phi. It really depends on how your phi is a function of time. Yeah, phi is a function. But remember, I think I erased that. At some point, I said the following, no? Dot delta T plus delta phi equals 0. Do you remember I said this? Yeah. I have to choose this delta T, and this delta T is in fact equal to minus delta phi over phi bar dots. And here you can see the problem. Well, if your phi is not even rolling, somehow you don't even know. There's no well-defined delta T anymore. Okay? So this is another way to say the same thing that I said earlier. Okay? You ready for exercise? Was there another question? Yeah. Yes. So there are different ways you can proceed. So here I have chosen a gauge, and in which case I have basically zeta and gamma. Those are my degrees of freedom. You could decide to actually not choose a gauge, but define instead gauge invariant quantities. It will be the analog of saying, I'm going to use electric and magnetic field instead of the vector potential. It will be the analog of that. And it turns out what you can show is that those gauge invariant quantities that you might choose, once you take the quantities and you evaluate in this particular gauge, those quantities would actually reduce to zeta and gamma. So there are two kind of different ways of, in the end, they are equivalent in terms of doing things. But there's two different kind of discussions that you can see in the literature. Yeah, does that answer your question? Thanks for asking. So yeah. Yeah, this is 5 bar, sorry. Good, thank you. This is 5 bar. Okay, so my questions now for you, okay? Let me not talk about the tensor power spectrum. Let's do the scalar. Tell me what is P zeta. You should be able to tell me what P zeta is by just matching what I have over there with what I have over there. Can you do it? Just do the mapping. It should not be a long calculation, but do it. You got it? And pretend for now, just pretend. Pretend this epsilon, even though it's a function of time, strictly speaking, this epsilon is just a constant. Just pretend it's a constant. M Planck is, of course, a constant. So these are just some numerical constant. So map what I have here to what over there, and then write down for me what is the power spectrum for zeta. You understand? Go ahead, do it. That would be our exercise for today, okay? You will again be deriving a very important result. And here, you should be able to get all the numerical factors right. Pretending epsilon is a constant. So just to amplify what I said, zeta as a function of k, eta, P zeta. Okay. So that's my definition for the power spectrum of zeta, just like the definition over there for phi. So write down the answer for me. What I'm asking you to do is almost just doing dimensional analysis, really. Okay? If you're not sure what's going on, just raise your hand. I'll come to you.